Hello, I am Tushar. Welcome to the presentation on implementation and study of a PAM system with transmitter, noisy channel, and receiver. PAM stands for Pulse Amplitude Modulation, where a series of pulses are modulated with the incoming signal. The incoming signal then passes through a channel where noise is added to it. The noise can be added not only due to the medium but also due to the electronics of the transmitter and receiver. The noise, which is mainly thermal noise, is fairly constant over a wide range of frequencies and hence can be modeled with a Gaussian noise model. The signal to noise ratio gives an idea of how strong the signal is as compared to the background noise. The distorted signal then reaches the receiver. Now the question arises how to demodulate the signal so as to recover the original signal. Herein comes the coherent detection technique, which implements a type of correlation so as to weed out the unwanted noise and achieve a good bit error rate so that the output regenerated bit stream matches the input bit stream as closely as possible. The system consists of three main parts: the transmitter, an additive white Gaussian noise channel, and a receiver. This is how the transmitter looks like. There is a random bit stream generator that generates bit stream messages, which are then mapped onto signal levels by the signal point mapper. The pulse shape generator generates pulse shapes, which in this project are of two types: the Polar non-return to zero and the Manchester non-return to zero. The pulse shape is then modulated with the signal levels by the transmit filter, and the resulting signaling waveform is transmitted onto the noisy channel. Let's look inside the transmitter. The random bitstream generator. I have used a Bernoulli random number generator to generate random numbers, which are then compared to see if they are not equal to zero. So we have a random bit stream of zeros and ones. The signal point mapper maps the incoming bit stream to certain levels. In this project, I have used 1 for true and -1 for false. The transmit filter imposes the incoming signal onto a pulse shape, which again can be either the Polar non-return to zero or the Manchester non-return to zero. The resulting signaling waveform is then transmitted onto the channel. The transmit sink's main purpose is to generate sync bits and transmit them to the receiver. They specify the start and the end of a bit interval. The AWGN, or the additive white Gaussian noise channel, simulates noisy channel. I have used a Gaussian random number generator to generate random numbers that simulates noise, and that is added to the incoming signal to create a noisy signal output. This is how the transmitter and receiver block combined looks like. So on the left hand side, so this part is the transmitter section, and transmitted signal comes onto this, additive white Gaussian noise channel, and the noise impaired signal coming out of the channel is received by the receiver. So all this part consists of the receiver. So first of all, it passes through the correlator. Here at the correlator, the signal is first multiplied by the same pulse shape that was used by the transmitter. The product is then integrated over 1-bit interval. The correlation function is controlled by the sync bits so that the correlation occurs at the right time. The output of the correlator is then sampled and held, and then they are compared to a zero level threshold to convert the incoming signal to Boolean values of either 0 or 1. These bits are then stored onto the bitstream buffer. The regenerated signal that is stored in the bitstream buffer is then compared with the input bitstream in order to determine the error bitstream, the error count, the array size mismatch, and the bit error rate. The bit error rate and the signal to noise ratio, which is also known as AWGN, can then be stored into arrays so that we can use them for plotting a graph of bit error rate versus AWGN. We can also find the theoretical value of bit error rate by using the Q function. Inside the receiver, we have the correlator, already seen, and how it helps to correlate the incoming signal with the pulse shape that was used at the transmitter side. The sample and hold, the bitstream buffer that stores the regenerated bits, and the bit error measurement block that is useful in comparing the regenerated bitstream with the input bitstream and counting the total number of errors and determining the bit error rate. And for typical values of message length, SNR, we get these waveforms. So this is the transmitted signal, this is the received signal, which definitely has noise added to it. Then this is the start sync bit, this is the end sync bit, this is the correlator output, this is the sample and hold output, and this is the regenerated signal. So everything looks pretty good here with the bit error rate 0. This is for the polar non-return to 0 pulse shape. Then we have the Manchester non-return to 0 pulse shape, and we have something similar over here. We see that the correlator output here at the Manchester non-return to 0 is quite similar to the one we had at polar non-return to 0. So both of these waveforms are quite similar. So the correlator output doesn't seem to depend on the pulse shape. This is mainly because the pulse shape is effectively multiplied twice, once on the transmitter and once on the receiver side, and hence becomes all once. The coherent detection technique is very powerful, and that where clearly the received signal is very noisy, and yet we have a very good regenerated or received bit stream. So this shows the power of coherent detection, that even though the SNR may be too low, we can still get a very good bit error rate. These are some plots of bit error rates versus the AWGN or the SNRs. We see that as the message length increases, the scatter plot closely approaches the ideal behavior, and also for lower values of AWGN, the spread or the variance in the bit error rate increases. So to summarize, we have found that the coherent detection is a very good technique, though costly and complex to implement, but it can be a very good technique to improve bit error rate, make it loosely dependent on the signal to noise ratio. So in digital communication designs where noise can be a very limiting factor, we can still have a very good design if we have a very good bit error rate, if we can still reproduce the original message well. And for this project I had used LabVIEW, which has turned out to be a very good tool and essential for all communication projects. Before I end this presentation, I would like to quickly show the front panel of my PAM system that includes the transmitter, the channel, and the receiver. So here are some typical values of the message length, the energy per bit, the bit interval. The pulse shape is rectangular, the sampling frequency is 10. Let's keep the SNR to 10 for now. The loop delay, as we'll see, determines how the waveform unfolds, how quickly the waveform unfolds. So if we run this, we see that the array size of the received bit stream and transmitted bit stream is equal, so the array size mismatch Boolean output is low. The ABNO or the SNR is 10, the standard deviation is 0.5, the samples per bit is 10, the error count is 0, and the bit error rate is also 0. We can change this to AWGN Manchester and see. And once again we find similar results with a bit error rate of 0 and similar correlated output. Now, just to illustrate what loop delay does, let us set the loop delay to 20. The default unit is milliseconds, and let us run this VI, and we see that the waveform unfolds slowly so that we can follow it. And unlike the previous run, it takes a longer time to complete the simulation, and it has ended, and we found the error count to be 0 and the bit error rate to be 0. So this is how the loop delay can help us to slowly see the waveform unfold and follow it as it changes its amplitude with time. I would like to reduce my SNR to around 5 to see how it affects the bit error rate. I run this simulation and I find the error count is 5 and the bit error rate is 0.05. So even though my bit error rate is not as good as before, but still it's good enough to have the output bit stream pretty close to the transmitted bit stream. We can also see at the same time that the received signal is not very intelligible to the eye, even though the system has done a pretty good job of regenerating the input bit stream. So coherent detection excels in regenerating the input bit stream even if its SNR is pretty low. So this project has helped me to realize the importance of coherent detection in digital communication design and the techniques that go into the design of a real-world communication system. Thank you.